Hello and welcome back to Deeksha Karnataka YouTube channel, and your second PUC first unit test is near. Maybe according to some of the dates it is starting from 10th of August, 9th of August, or in some cases it might start a little later on in the month of August, but it will happen in the month of August. So here we are bringing you the complete revision for all important questions for second PUC unit test. Today I am going to discuss all important questions for physics. It will be one short video. Along with that, we will also take a live class. I will personally come and take a live class, and any chapters, any topics that you want to be specifically discussed, please mention that in the comment of this video, so that later on I can check and I can include that in my live discussion. Okay, so what are all the chapters that we are going to discuss in today's session? Let's look into that. So mainly we are going to cover the three chapters: electric charges and fields, electrostatic potential and capacitance, and current electricity. Okay, also your unit test will happen only for physics. It will be 35 marks test, right, and the marks will go to board. Okay, your marks will be entered in the SATS portal, and it will be recorded specifically for all the subjects. It will be recorded maths and language subjects. The 20 marks that you have as the college marks, that while calculating that marks, these marks will be considered as well. And also in case your academic performance is somewhat, if you doubt that your final marks was not according to your expectation, you can show that my unit test result was good, my midterm result was good, but somehow my final result was not good. But the question paper will be set by your college, respective colleges only. Okay, so let's look into the first chapter, electric charges and fields, and question pattern will be half of generally whatever you are expecting. The exact blueprint will be shared by your respective college. If they have not shared, you can go and ask your teacher that sir, please share the blueprint. It can vary a little bit based on college to college. Some prefer to give 7 MCQs, some prefer to give 8 MCQs, 4 and so on, right? But everything will be there: MCQs, fill in the blanks, 2 marker, 3 marker, 5 marker derivative based question, and 5 marker numerical. 1 numerical you have to do. Every question will be included in this 35 marks paper. So let's start with the MCQ first. We are going chapter wise. So first, electric charges and fields chapter. The SI unit of electric charges, very easy you might think, okay, but still many students find it difficult and do not answer it correctly. The SI unit of electric charge is coulomb, right? The total electric flux through a closed surface in air is equal to 1 by epsilon naught times the total charge enclosed by that surface. This is the statement of obviously Gauss's law in electrostatics. It is not magnetism. Gauss's law of electrostatics. Okay, I think both A and C are correct. No, sorry, my mistake. I read that Gauss. It will be Gauss's law in electrostatics, not Coulomb's law in electrostatics. Okay, this is Coulomb's law, not Gauss's law. Okay, so Gauss's law in electrostatics states this. Now next question: electric field due to an electric dipole at a distance r from the axis of the dipole is directly proportional to r cube, directly proportional to r square, inversely proportional to r cube, inversely proportional to r square. Now you have to remember that electric field due to an electric dipole is inversely proportional to 1 upon r cube. Okay, inversely proportional to 1 upon r cube. Very simple, easy question, but sometimes student by mistake or when they are in a hurry, they by mistake mark option A as correct. So be careful, read the question carefully. That's what my suggestion to you as well. Whenever you are answering MCQ questions, whenever you are answering fill in the blanks question, read it twice, so that excuse me, so that you are sure, okay, this is the answer, this is the question, this is the answer for that. The SI unit of electric flux is, what is electric flux? Electric flux is electric field line per unit area. So you can say that electric flux is basically E into area, right? Electric field into area. What is electric field? Newton per coulomb and area is meter square. So, it will be Newton meter square per coulomb. So, correct answer is option C. Okay. So, if you have any doubt, just verify it. Okay. So, this is the unit. Here they have changed the order to confuse you. So, Newton per coulomb meter square is multiplied. So, Newton to the power C to the power minus 1 meter to the power plus 2. So, that will be the answer, right. Charges are conserved for open system, isolated system, any system, no system. Now, you may have heard conservation of charges, and you might think that conservation of charges is applicable for any system, but that is not correct. Conservation of charges are only applicable for isolated system. System is isolated, then only the charges will be conserved. If the system is open system or any system, it will be not conserved. Okay. Be careful while with this type of questions. The value of the basic unit of charge is 1.6 into 10 to the power of minus 19 coulomb. Okay, this is the charge, is basically E, charge of an electron, that is the basic unit of charge. Now, next, two electric field lines can never intersect, always intersect, may intersect, always perpendicular. Two electric field lines can never intersect, Okay, the SI unit of surface charge density is, surface charge density is what? Surface charge density is basically given by, surface charge density is given by sigma equals to total charge divided by surface area, right. Charge is, what is the unit of charge? Unit of charge is coulomb and area is meter square. So, surface charge density is coulomb per meter square, that is option B. Next question. The SI unit of electric field, very easy question. SI unit of electric field is coulomb, Newton per coulomb, right? Newton per coulomb or volt per meter. Newton per coulomb or volt per meter. If the same question is asked from the next chapter, then it will be volt per meter. Okay, the volt per meter is not discussed in this particular chapter, but it is discussed in the next chapter. If you remember, electric field E is given by dV by dl. So, that is another unit. Volt per meter is also electric field, voltmeter is not the electric field. So, either Newton per coulomb or volt per meter, both are the unit of electric field. The angle between the dipole moment and electric field at any point on the equatorial plane. So, on the equatorial plane, so this is the dipole. So, suppose this is negative, this is positive. So, electric field will be in this direction, and dipole moment is from negative to positive, it will be in this direction. So, the angle is always 180 degrees, angle is always 180 degree. On the axial case, the electric field will be also in the same direction. So, electric field and dipole moment will be on the same direction. So, for axial it is 0 degrees, for equatorial plane it will be 180 degrees. Now, let us look into some fill in the blanks. Fill in the blanks also I have seen students making mistakes because the less number of chapters, there will be fill in the blanks from all the chapters. Also, what you have to consider is that while answering, read the sentence. Okay, sentence Salpa read Mari, and if you cannot make any sense of this sentence after you put the word into it, then definitely it will be a wrong answer. Okay, I am giving you one example. One of the basic properties of electric charge is dipole, suppose. So, it does not make any sense, does not give you any meaning. So, one of the basic properties of electric charge is not a dipole, right. So, what is the option? What could be the answer? One of the electric basic properties of electric charge is never, no dipole, never. Quantization, what about quantization? Is it making any sense? Yes, it is making some sense. So, basically it will be quantization. So, one of the basic properties of electric charge is quantization. A pair of equal and opposite charges q and minus q separated by a distance 2a is. So, a pair of equal opposite charges q minus q separated by a distance 2a. So, q plus q minus q separated by a distance 2a, what is it? It is a dipole, it is a dipole. the electrostatic force between, so dipole is done, quantization is done. So if you are sure of some answers, just strike them off to be sure that okay, this this one you have already answered it. Some student mark it under it so that they can identify it whatever way you are comfortable, that is fine. So if you have finished it, you mark it so that remaining options only will be fill in the gaps. Okay, there will be one extra option. The electrostatic force between two charges is maximum in. The electrostatic force between two charges is maximum in never, vacuum, zero, always. So even if you don't know the answer, if you see the electrostatic force between two charges is maximum in never, does not make any sense. Okay, maximum in vacuum, it's a medium, it makes a sense. Okay, zero also does not make any sense, always also does not make any sense. So vacuum is only making a sense over here, it's a medium. So electric field, electric force between two charges is basically maximum in vacuum. We know that that is the case in any dielectric medium, it decreases, right? So it will be vacuum. Electric field inside a charged spherical conductor is, so out of the remaining options, never or zero and always, so it will be basically 0. Okay, so answer will be 0. So electric field inside a charged spherical conductor is 0. Two electric field lines will always cross, never cross. Now there will be one option where both the remaining options will make sense. So that is basically a particular distractor. Okay, so there will be some cases where you have to be very careful and you have to know the answer for sure. For example, two electric field lines will never cross, even always also making a sense over here, but you have to know in this particular case. Otherwise most cases 4 out of 5 you will be able to answer just by checking whether it is making a sense or not. Only 1 or 2 maximum 2 where you might have a confusion. For that you have to be, either you wait a little bit, calm your nerves down, and then you can answer that question. Here it will be never cross. Okay, now let us see. Write Coulomb's law in vector form, explain the terms. This is one of the very favorite question of all the teachers, amongst the teachers who are framing the question paper for your unit test. So there is a high chance either Coulomb's law or Coulomb's law in vector form. Now there is a basic difference between Coulomb's law and Coulomb's law in vector form. In Coulomb's law in vector form, you have to draw this diagram. There is one more diagram given in your textbook. You can draw that as well. I have simplified the diagram for you. You can draw this diagram as well, and you have to mention this is this as your r cap vector. This is as your r cap vector. Also the force on this is F12, force on this is F21. Okay, so this one you have to show, these arrows you have to show, and you have to show this r cap. Also, if you want to download the PDF of this lecture along with all everything, so question and the solution, please join our WhatsApp channel. The paper will be shared in our WhatsApp channel, so don't wait, click on the link given in the description of this video and join our WhatsApp channel today. Now write Coulomb's law in vector form, explain the terms. So Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between them. Okay, the force acts along the line joining them. If you want to add that, that is also very good. Okay, also you can write them in points 1 and 2. Coulomb's law in vector form is given by F12. You have to write this. F12 equals to 1 by 4 pi epsilon. You should not write only simply vector F, that is not correct. Okay, you have to use F12, and also you have to draw the diagram and show what is F12, what is F21. That is also very, very important. Without the diagram, the teacher can give you 0 marks, right? For this question, diagram is compulsory. Okay, diagram is compulsory. So in some cases diagrams are compulsory, and it is also mentioned in the board's manual that when checking a question, if the question required a diagram or some numerical formula. If you are not writing them, then you are entitled to get 0 marks. Okay, so be careful. And F12 equals to 1 by 4 pi epsilon naught Q1 Q2 by R square R cap. Okay, and that is equals to minus F21, that is equals to minus F21. Okay, so both everything F12 is plus, F21 is minus, everything you have to mention, and along with this diagram also you have to explain the terms. Q1 Q2 are point charges, epsilon naught is the permittivity of free space, R is the distance between Q1 and Q2, so that is also shown in the diagram. R cap is the unit vector. So along with the diagram you have to give the statement and explain the terms. Okay, this is very very important because you are going to write this exam for the first time. Most of you are writing this first time. In some colleges they already have taken monthly tests, I know, but in that case, many cases teachers do not explain how to write answers. That is very very problematic for many of you. So that's why I am here to explain how to write the answers. State and explain Gauss's law in electrostatics. This is also one of the very common questions. Sometimes it can come as a simple 2-mark question, sometimes it can come as a part of a 5-mark question. Okay, in that case they only ask you state a Gauss's law. Okay, so be careful, this can come in either as a 1-mark question, in 5-mark numerical question or derivations. Not numerical, sorry, it can be a part of a derivation, it can be a part of a simple single question as well. State and explain Gauss's law in electrostatics. Gauss's law states that the total electric flux passing through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. Okay, 1 by epsilon naught times the net charge enclosed by the closed surface. Explanation: phi equals to q by epsilon naught, or E dot ds equals to q by epsilon naught. Q is the total charge enclosed by a surface S. You can draw a diagram. Okay, you can draw a diagram. This is optional, but if you draw a diagram it will be very very good. Teacher will know that you have understood the concept and you have basically writing it from your own and you are not copying it from your friend's notebook, right? Next question. Sketch the electric lines of force due to a point charge if q is less than 0 and number 2 q is greater than 0. This is a very common question. It is given in your model question paper, one of the model question paper. It might come in your, if some teachers think that this is an interesting question, easy question for students, but still not super easy. Student might face difficulty. Some students who does not study physics, they might feel this difficult. I have seen this. Okay, some students, they are doing well in biology but they are not doing well in the physics. So now when you are talking about plus q and minus q, okay, so for charge less than 0, that is first case, all the arrows will be inward. Okay, for all the arrows will be inward. Okay, so be careful and mark the arrows properly. This basically you have to draw a charge at the center and then you have to draw the lines. That's it. And but main important thing is the arrows. If you are drawing the arrows wrong, you will not get good full marks. Okay, similarly for plus q, if the charge is greater than 0, all the field lines will be outward. So you have to draw the lines like this, right? Right. Next question. The charges are additive in nature. Explain. This is also important question. This is one of the property of charges. Also charges are quantized, charges are additive, charges are so charges are additive, charges are quantized, charges are conserved. So these are the 3 properties of charges, right? So any one property might come as an explanation, but additive in nature is more common. Okay, if a system contains 2 point charges q1 and q2, the total charge of the system is obtained simply by adding algebraically. Okay, so if you add the charges algebraically, then that it will give you the total charge. That is, charge add up like real numbers, they are scalars like the mass of a body. Okay, so charges are basically scalars. also you have to give one example, very important. Not only the writing, you have to also give one example. The total charge of a system containing 5 charges plus 1 plus 2, you can take any charges, does not matter, you can take 10, 20, 30, does not matter, but try to keep some of them plus, some of them minus, and final charge will be just addition, algebraic addition of them. Okay, so plus 1 plus 2 plus minus 3 plus 4 plus minus 5. This is how I have written it. You can write it in this fashion, and the total charge is minus 1. Okay, so whatever is the unit, suppose this is all in coulomb, then this will be 1 coulomb. Okay, you can take any charge, any values, does not matter, only you have to add them and show that whatever is the total value, right. Some students try to write it, memorize this value as well, which is not correct. You have to, you can use any values. Now next, derive the expression for the torque on an electric dipole placed in a uniform electric field. Very important. This is a VVI question. Okay, and this is a 3-mark question, by the way. If you observe that we have now moved on to 3-mark question. Previously all the questions were 2-marker, now it is a 3-marker question. So first you have to draw this diagram. Again, this question, to answer this question, the diagram is compulsory. A dipole is there, an electric field is there. Now if you keep a dipole in an electric field, what will happen? It will experience force, charges will experience force. The positive charge will experience force in the direction of the electric field. The negative charge will experience as a force in the direction opposite to that of the electric field. Now what is the value of this force? The force is basically given by charge times electric field. This is the magnitude. Okay, so any direction is opposite, but the magnitude of the force is constant. Now two equal and opposite forces acting on a system, right? Two equal and opposite forces are acting on a system, so this will basically experience as a torque. Now what is the value of the torque? How to calculate torque? To calculate torque, if you remember, torque is basically given by force into distance. Cross product, obviously cross product. We are just writing it in the scalar term now. We will convert it into vector later on, but now we are first writing it in scalar form. Force into distance. What is the distance over here? Distance is basically the distance between the two parallel forces. Distance between the two parallel forces, this is d, right. Now this is a right angle triangle. If you see, this is a right angle triangle and this is 2a. This angle theta is given to you. This angle theta is given to you. So if this angle is theta, from there you can say this angle is also theta. Now if you want to find the value of d in terms of 2a, that is our target, value of d in terms of 2a. So this is theta, this is perpendicular, this is hypotenuse, right angle triangle, right, hypotenuse, and this is perpendicular. So from there I can say sin theta is perpendicular by hypotenuse, right, or d equals to 2a sin theta. Okay, so we just need to put those values, everything here. So q, F is q into E into d is 2a sin theta, or E into q into 2a sin theta. Now what is q into 2a? Q into 2a, this is a dipole, right? This is the charge and this is the distance between the charges. So q into 2a is basically the dipole moment. Q into 2a is the dipole moment, EP sin theta. Every stage you have to mention this, you have to mention everything, you cannot skip this. Okay, so here you have to mention P is equal to dipole moment equals to Q into 2a. Okay, you have to mention that. So now torque is basically EP sin theta, or you can the common form in the textbook that we write is P first, E second, PE sin theta, or in the vector form it is P cross E. It's a cross product of the dipole moment an electric field. In vector form you have to write in vector form. Very simple, easy derivation. Only thing you just need to remember the basic definition of torque and what are all the forces acting, and basic geometry from where you can calculate the distance. That's it, right? I hope that clears. Now let's move on to the next question. Write any three properties of electric charges. There are only three properties of electric charges. Now this question can come as a 2-marker question as well. In that case they will mention write any two properties of electric charges. Okay, so you have to remember there are only three properties of electric charges. Additivity of charges, charges can be added like a scalar. Quantization of charges, all charges are integral multiple of smallest charge E, right, charge of an electron. Conservation of charges, total charge in an isolated system is conserved. Okay, now while writing this I request you to add these small lines in this question. Okay, many students just write additivity of charges, quantization of charges, conservation of charges. Now what is the meaning of that? You have to write it little bit, right? So you have to write that charges can be added like scalars, or charges can be added algebraically. Quantization of charges, all charges are integral multiple of a smallest charge E, okay, and conservation of charges, total charge in an isolated system is conserved. Just small explanation, nothing difficult, nothing long, okay, small explanation is sufficient, and 3 marks you will get for that, right? So write this explanation. Next is, what is the electric dipole? Define electric dipole moment, give its direction. This is a simple question as well, 3-mark question. Dipole, two equal and opposite charges separated by a small distance is known as electric dipole, and then it should accompany with a diagram. It is very essential. The diagram is not compulsory, but if you draw the diagram then you are basically telling the teacher that I am aware what is a dipole, I am a good student. Basically what is, when you write a paper, you have to understand that when you write a paper, even the teacher does not know you, or even if they know you, okay, you are leaving a impression to that teacher, okay, how well you have prepared, okay, how good the student you are. So this is basically a mirror of you in front of the teacher. Okay, so teacher can understand, okay, you are a good student. Okay, in some cases if you write your answers perfectly, even if you make small mistakes, the teacher will ignore that and I will give you full marks, because thinking that these mistakes can be ignored, he is writing the paper beautifully so far, so I will ignore this mistake and I will give him full marks. So that is how you build up something, when even if the teacher does not know you, okay, or even you does not know the teacher, you don't know the teacher, so still you can make an impression of yourself, and these small additions actually makes an impression in front of the teacher, right? So dipole moment, now dipole definition is done. Dipole moment, electric dipole moment is the product of magnitude of one of the charges and the distance between them. It is a vector quantity, so you have to understand dipole moment is the, you can write the expression for as well, P is equal to Q into 2A. Okay, it is a vector quantity. The direction of dipole moment is from negative to positive charge. So the dipole moment is from negative to positive charge. This is the dipole moment. Okay, it is always from negative to positive. Write 3 properties of electric field lines. Now I have seen this question coming as a 5-marker optionally. Occasionally in some colleges they do prefer this question as a 5-marker, because they think that this is some easy question, so student will be given some chance to score some easy marks. So that's why I have included 5 marks, but it is actually a 2-marker or 3-marker. Most commonly 3-marker, but it can come as a 2-marker as well. So this is a 2-marker or 3-marker and even 5-marker question as well. I have given you all the 5 options, and this is a very important question as well. Okay, this is also a very important question. There is a 90% chance that this question will come in one form or another. Okay, electric field lines may start from positive charge and end at negative charge. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. two electric field lines are never intersect each other, the electrostatic field lines do not form any closed loops, and electric field lines in free space decreases as we move in the direction of electric field, and vice versa. So, if you move in the direction of electric field, it decreases. If you move opposite to the direction of electric field, it increases. That is how these are the properties of electric field lines, and do not confuse them with the properties of electric charge. Electric charge and electric field lines are different, and their properties are also different. I have seen students writing this answer for that question and that answer for this question. So, do not confuse them. Okay, download this PDF, and if you want, you can take a printout of this particular 2 pages and keep it in your desk, and you have to remember these. Okay. Derive now let's move into the 5 marker section. Derive the expression for electric field at the point on the axis of a dipole. Very important, one question from the dipole is very common, and there is a high chance that it will come. So, first let me draw the diagram. So, here we have a plus q and here we have a minus q. Okay. This is the dipole, the distance between them is 2a, and what else? We are trying to find the electric field at a distance at some point, say P. At this point we are trying to find the electric field, and the distance from the center of the dipole. Now, dipole has 2 charges, right? So, whenever I said distance from a dipole, basically that means the distance from the center of the dipole. So, the distance, say, is r. Okay, the distance from the center of the dipole is r. Now, this distance is 2a, so this will be a and this will also be a. Okay. Now, if you remember the case where we have one single charge q and we are trying to find the electric field due to one single charge, what was the formula? Electric field was given by k q by r square, right? That was the formula for a single charge. This is for your reference, you do not need to do that in the exam. So, what is the electric field due to this positive charge? So, electric field due to the positive charge is given by E plus. Now, if you see what is the distance between plus charge and this P? The distance between this plus charge and this P is basically, this distance is, total distance is r minus a. So, this will be r minus a. R minus a is the distance from the positive charge at the point P. So, positive E positive is basically given by k q by r minus a whole square, right? K q by r square. What is the, similarly we can say that E negative will be k q by r plus a whole square. Do not memorize everything. Do not memorize everything. Try to remember whatever is necessary, and some formulas you have to memorize. Okay. So, if you memorize everything, then there is a chance that you will forget. So, the distance from this negative charge will be a plus r, that is r plus a. Okay. So, that is why it is r plus a, that is why it is r minus a. So, you have to understand this fact, then only it will be very easy for you to write the same thing in your exams. Now, what is the total electric field? Total electric field or net electric field. Now, you have to understand that what is the direction of the respective electric fields. So, the positive charge will have a electric field in this direction, E plus, right? The positive charge will have a outward electric field, and the negative charge will have a electric field in this direction, E minus, right? E minus will be in this direction. Now, which one will be greater? Which electric field will be greater? Now, as you can see that the distance from the positive charge to the point is small compared to the distance from the negative charge, right? So, E positive will be greater, E negative will be lesser. So, when calculating the net electric field, what you have to do? You have to subtract the smaller one from the bigger one. Okay. While writing the electric field, do not use any sign. Identify which one is bigger, which one is smaller, then subtract bigger from the smaller from the bigger, sorry. So, now put the values kq by r plus r minus a whole square, r minus a whole square minus kq by r plus a whole square. Okay. So, now kq we can take common. Now, let us do the multiplication, r minus a, r plus a. So, it will be r minus a, r plus a, both were square. So, it will be square outside. Now, this will come over here. So, r plus a whole square minus r minus a whole square, right. Now, let us put that value kq. Now, what is r plus a whole square minus r minus a whole square? So, a plus b whole square minus a plus b whole square, a plus b whole square minus a minus b whole square, which is basically 4ab. So, 4ra. Okay, this is a formula, right. If you forgot, you have to remember that a plus b whole square minus a minus b whole square is 4ab. Okay, and a plus b whole square minus plus a minus b whole square is 2 into a square plus b square, right. Now, 4ra. Now, if you see that r minus a, r plus a, that means it will be a plus b into a minus b, that will be a square minus b square. So, it will be r square minus a square whole square. Okay, a square, r square minus a square whole square. Now, you have to compare that. So, now you have to simplify this. E net is basically coming out to be kq 4ra by r square minus a square whole square, right. Now, here you have to do one small approximation. Okay. Before going into the approximation, let me write one more line. So, 2r q into 2a divided by r square minus a square whole square. So, what I have done is this 4ra I have divided into two parts, 2r into 2a, and that 2a I have multiplied with q, right. 4 I can divide into 2 into 2. So, one of the 2 I kept with r, another 2 I kept with a, and this 2a I multiplied with q. Everything is multiplication, right. Why I am doing that? Because this will give me the dipole moment of the dipole, right. Q into 2a is the dipole moment. So, also from this expression, what we can say that for a dipole, r is very greater than a. Okay, the definition of the dipole, if you remember, the distance between the charges is very small, right. So, distance between the charges is very small, means r is very greater. So, we can basically ignore this a square, we can ignore this a square, but we cannot ignore this small a. Okay, here it is multiplication, here it is addition or subtraction. So, addition and subtraction cases, small number can be ignored. For multiplication cases, small number cannot be ignored. Okay. So, E net will be k into, so 2r into q into 2a is the dipole moment, and if you ignore this a square term, you will get r square whole square, that will be r to the power 4. So, here you will get equals to 1 by 4 pi epsilon naught 2p by r cube. Okay. So, now this is not over yet, there is one more step to do. What is that step? What is the direction of the dipole moment? Dipole moment is from negative to positive. Dipole moment is from negative to positive. What is the net electric field here? Net electric field is in this direction. Why? Because positive is greater, right. So dipole moment and net electric field both are in the same direction. So we can write E net vector will be 1 by 4 pi epsilon naught 2 p by r cube, and p will be same. So E net is 1 by 4 pi epsilon naught 2 p by r cube, right. This is how you should complete the derivation. Simple derivation, practice is 2-3 times and try to understand it. Once you understand it, there will be no difficulty for you to replicate the same in the exam, and this is also very important for your board exam as well. Okay, there is a high chance there will be a derivation from the chapter electric charges and field, particularly this year. Okay, derive an expression for the electric field at a point on the equatorial plane of the dipole. Same concept here. Now we are going to do for a equatorial plane. So here we have a dipole minus q plus q. Okay, let me use this. This I am using in the opposite sense. It will be little easier in the drawing purpose, nothing else. Okay. You can use this also in the previous case, it will not, the result will not change. This is the equatorial plane. Equatorial plane means it is the plane which bisects this dipole into two halves, two equal halves. That means this distance and this distance are same. Okay. Now you are considering a point here, this distance say r. Okay, equatorial plane. So distance is always measured from the center of the dipole. So this distance is r. Now what you have to do, you have to find the, again you have to do the calculation of the electric fields due to individual charges. Now positive charge will have an electric field in this direction. This will be the E plus. E plus will be away from the positive charge, and the negative charge, electric field due to the negative charge will be in the direction of the electric negative charge, right. So it will be E minus. Now what is this distance? This is A, this is R. So this is a right angle triangle, this is a right angle triangle. So what is this side? This side will be square root of R square plus A square. Okay. Hypotenuse, Pythagoras theorem. Now if you consider this angle to be theta, okay, this angle will also be theta. Why? Because this is an isosceles triangle. Both this is a perpendicular bisector. Perpendicular bisector always gives you a isosceles triangle. That means both sides should be same and both base angle will also be same, right. Now if you consider one axis along this, one axis along this, okay, all the force. So if you consider this is one axis, this is one axis, x and y. So if you see that this plus will have a component in this direction and one in the positive y axis, whereas the E minus will have a component in this direction and one along the negative y axis, right. So one along the positive, one along the negative. So negative will cancel each other, both of them will add up along the x axis. So net electric field will only be along the x axis and not along the y axis. Also one more important part to remember in this particular derivation, that this distance is equal to this distance. So distances are equal in both cases. So distances are equal means k q by r square for both positive and negative, magnitude wise the electric field will be same, right. So we can write here E positive equals to E negative equals to E, and that is equals to k q by square root of r square plus a square whole square, right. So from here we can say E equals to k q by r square plus a square, okay, whole square and square root they cancel each other. This is the distance, right. This was the distance, r square plus a square was the distance in this particular case. Maybe you are not able to see this. Let me write it little bigger font so that you can see that. Right. So this is r square plus a square. So this is the distance, and this distance is equals to this distance, both distances are same. So from there we can say that this is basically E is equal to kq by r square plus a square. Now both electric fields are calculated. Now what? Now we have to find the x component. How to do that? So as I said, this angle is theta. Okay, so this is this and this are parallel. Okay, so this will be similar angle. This angle will also be theta. Now this angle is theta, so this angle will also be theta. This is a z kind of symbol, so this angle will also be theta. Right? So what is the net electric field? Net electric field is basically E plus cos theta plus E minus cos theta. Both cos component, because angles are same, so both cos component. Okay. Now E plus E minus both are equals to E, so we can write this as 2E cos theta. Okay, 2E cos theta. Now what is the value of cos theta? Now we have to come back to this triangle. We have to come back to this triangle. This triangle, as you can see here, we have, this is the hypotenuse, this is the base. Base is a and hypotenuse is r plus a square, r square plus a square square root. So cos theta is base by hypotenuse. So there was a thing that I told you in my previous lectures. If you have missed that, some people have curly brown hair turned permanently black. Some people means sin equals to p by h. Okay, curly brown hair, curly means cos, brown means base by hypotenuse, right? So that's how you can remember it. So there is a important video called bridge course. So if you have missed that, go and check that out. There I have discussed this. So 2 into E is this kq. So as you can see, the approach for this one and the previous one are completely different, right? And what is the cos theta? Cos theta is a by square root of r square plus a square, right? Now again we have to simplify this. K is come out, we get q into 2a, this 2 and a is multiplied, right? And in the denominator we have r square plus a square to the power 3 by 2. Why 3 by 2? Here it is r square plus a square to the power 1, and here it is to the power half. So 1 plus half is 3 by 2, right? Now let's continue with the derivation. So E net equals to K. Now what is Q into 2A? Q into 2A is P divided by r square plus a square to the power 3 by 2. So it will be r square to the power 3 by 2. Why? Because r is very greater than a. Same condition. Okay, so r square to the power 3 by 2 is what? So E net equals to Kp by r cube, right? E net equals to Kp by r cube, or you can say E net equals to vector E net equals to minus K. The last stage you have to write the value of K, that is 1 by 4 pi epsilon naught P vector by r cube. You have to do that for the previous case also. Now why this is negative? Why I put this negative sign over here? The net electric field is in this direction. What is the direction of dipole moment? Dipole moment is from negative to positive. So dipole moment is in this direction. So electric field and dipole moment, they are in the opposite direction. So the angle between electric field and dipole moment is 180 degrees. Okay. So angle between electric field and dipole moment is 180 degrees. Right? Now next derivation, there are a lot of possible derivations from this chapter. That's why we are doing this derivation. In the next chapter there is only one derivation possible, so we will do that derivation as well. Derive the expression for the electric field at a point due to an infinitely long thin uniformly charged straight wire using Gauss's law. So here we have to do the line charge. Okay, so here we have a line charge. Okay, the line charge density, say lambda, positively charged, assuming positively charged, negative is also fine, but we are assuming this as positively charged. Now we are trying to find the electric field at some point P. So how to do that? First of all, you have to apply Gauss's law, you have to construct something called Gaussian surface. So to construct Gaussian surface, what we have to do? We have to construct a cylinder here. This is cylindrical symmetry. Straight line is a cylindrical symmetry. So here we have to construct a cylinder having a radius equals to the same distance r. Okay, this is not P, this is P, right? We are trying to find the electric field here. So you have to construct a cylinder, Gaussian cylinder having a radius of r. Okay, and it the line should pass through the axis of this cylinder. Symmetry is always better. Now if you consider this is a symmetry, electric field due to this or this or this or this, electric field will be same. Everything will be at the same distance, right? So electric field due to this line along the cylinder, surface of the cylinder will be constant. That is very, very important. Also we have to consider the length of the cylinder to be L, which we are just assuming. Length of the cylinder to be L. This is a very tricky derivation, but easy derivation. Okay. Now what is the charge enclosed in this cylinder? Charge enclosed is given by the line charge density times the length. This is the length, right? This is the length. Line charge density is given here, lambda. So charge enclosed is Qn equals to lambda into L. Now from Gauss's law, okay, from Gauss's law we can write integral E dot dA equals to Q enclosed by epsilon naught. Okay, now what is, as I said, E is constant along the surface. E is constant along the surface. So E will be coming out of the integration. E dot dA will be become E into dA, integral dA equals to Q enclosed by epsilon naught. Okay, now we have to put the values. E into dA is what? dA is the surface area of the cylinder. So what is the surface area? Now this surface we will not consider because electric field and the surface area are in perpendicular. So E dot dA will be 0. So if you are wondering, these surfaces are not considered, only the curved surface is considered. Okay, so what is the area of a curved surface for a cylinder? It is 2 pi RL, 2 pi RL. Okay, equals to, now what is Q enclosed? Q enclosed is lambda L by epsilon naught. So L cancels. From this you get electric field is given by, so 2 pi R will go other side, you will get lambda by 2 pi R epsilon naught. Now I like to write this particular form as 1 by 4 pi epsilon naught, 2 lambda by epsilon naught, 2 lambda by R, sorry. I like to personally like this form. Okay, this is also fine. This is just for competitive exam purpose because this gives you a constant value. Okay, so this is one or this one, whatever you leave you will get full marks. Very simple derivation, only you have to draw the diagram properly and if possible explain the diagram. Okay, otherwise this much is sufficient. Also you have to mention that lambda is the surface line charge density. Okay, now let's move on to one numerical question. 2 point charges plus 4 nanocoulomb and plus 8 nanocoulomb are placed at the points and A, B respectively, separated by a distance 0.2 meter in air. Find the magnitude of the resultant electric field at the midpoint O. So, here we have 2 charges plus 4 nanocoulomb and plus 8 nanocoulomb. Okay, and we are trying to the distance between them is 0.2 meter. So, if you see that already SI unit conversion is given over here, you do not need to convert it, but you have to find the electric field at the center. Electric field at the center. Okay. So, electric field at the center means it is similar to that of the dipole. So, plus 8 will have in this direction E plus 8 and plus 4 will have a electric field in this direction plus 4. Now, distances are equal, both side will have a 0.1 meter and 0.1 meter distance, right, distances are same. So, which one will have the greater electric field? E plus 8 obviously, because of the higher value of the charge, right. Now, that is the major thing, but otherwise it is basically a dipole. And what is E plus 8? E plus 8 is basically given by KQ by R square, K Q, say Q1. K, what is the value of K, by the way? K is 9 into 10 to the power of 9, 9 into 10 to the power of 9. Right. What is Q1? Q1 is 8 nanocoulomb. 8 nanocoulomb means 8 into 10 to the power of minus 9. What is R? R is 0.1 meter, 0.1 meter. So, 0.1 whole square. So, 10 to the power of 9, 10 to the power of minus 9 cancels. Okay. 7, 9 8s are 72 and divided by 0.01, that is 7200 Newton per coulomb. This is the electric field due to plus 8. So, what is the electric field due to plus 4? Electric field due to plus 4, same formula, only the charge will be different. So, 9 into 10 to the power of 9 into 4 into 10 to the power of minus 9 divided by 0.1 whole square, which will be 3600 Newton per coulomb. Okay, basically it will be half of that. Charge is half, so the electric field is also half. So, what is the net electric field? As you can see, the net electric fields are opposite direction. Positive charge will always repel. So, if basically what you have to do, you have to put a 1 unit positive charge at this point to find the direction, right. So, to find the direction of electric field, you always need to put a unit positive charge at the point and then see whether it will attract or repel. So, it is getting repelled by both sides. So, they are opposite direction, plus 8 and plus 4 are in the opposite direction. Which one is greater? Plus 8 is greater. So, the net electric field is E plus 8 minus E plus 4, that is 7200 minus 3600. So, the net electric field is 3600 Newton per coulomb. This is the part 1. Part 1 of the answer. Now, what is the part 2 of the answer? What will be the magnitude of resultant electric field at O if plus 4 Newton nanocoulomb is replaced by another plus 8 nanocoulomb? So, if you replace this plus 4 nanocoulomb with another plus 8 nanocoulomb, so this side we have plus 8, this side we also have a plus 8. So, both sides have the same charges. So, electric field at the center, this will have E plus 8, this one will also have the E plus 8. So, they will cancel each other. So, the net electric field in this particular case will be 0. Okay, this is part 2 of the answer. Okay, you have to answer both part. If you miss this part, there will be marks deduction. Okay, so 3600 Newton per coulomb and 0 are the answers for this question. Now, next question, last question for this chapter. 2 point charges 5 microcoulomb and minus 5 microcoulomb are located at A and B respective separated by 0.2 meter in vacuum. Again similar question. but here you can see that charges are opposite. That means it's like a dipole, but the distance is slightly longer. What is the electric field at the midpoint O of the line joining the charges? Again, same question. This is a very common type of question from this chapter. Now there are a lot of difficult questions are there, but I will try to cover some of them in my live session. As I told you that I will be taking a live session, there I will be doing some questions, some more numericals, some more MCQs as well, right? So here it is, the distance is 0.1, here also 0.1. And if you want any specific question to be answered, please mention that in the comment of the video, sir, I want this style of question to be answered. I will cover that. Okay. Now let's see. What is the electric field at the midpoint O of the line joining the charges? What is the electric field? So electric field due to -5 microcoulomb is given by, both will be same, right, k q by r square, but here positive will be in this direction and negative will also be in this direction. Okay, positive and negative both will have the same magnitude because the charges are same, but the direction will be in the same direction. Okay, so k q by r square, so it will be 9 into 10 to the power of 9, charge is given 5 microcoulomb. Micro means 10 to the power of -6 divided by 0.1 whole square. So it will be 5 9 is 45. 45 into 10 to the power of 3 divided by 0.01, that is 45 into 10 to the power of 5. Okay, this is basically go up and become 10 to the power of 2. So Newton per coulomb. So this is the field due to E negative. Similarly, E positive will also have the same electric field and in the same direction, that is 45 into 10 to the power of 5 Newton per coulomb. Same electric field. Okay. So what is the net electric field? In this case, net electric field will be added. So this is the main thing that you have to understand. So in this case, net electric field will be added, 45 into 10 to the power of 5 plus 45 into 10 to the power of 5, that is 90 into 10 to the power of 5 Newton per coulomb, or you can say 9 into 10 to the power of 6 Newton per coulomb. Okay, this is again answer number 1. Answer number A in this case. If a negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the test charge? So part B, so force experienced by the test charge is Q into E net. What is the Q? Q is 2 nanocoulomb, 2 into 10 to the power of -9, and E net is 9 into 10 to the power of 6. So it will be 18 into 10 to the power of -3 Newton. Okay, so this is the force experienced by the test charge. So 9 into 10 to the power 6 Newton per coulomb and 18 into 10 to the power of -3 Newton. Okay, so this is the end of this first chapter, and now we will move into the second chapter. The second chapter of our discussion today is electrostatic potential and capacitance. So let's continue with the MCQs first. First question, the angle between the equipotential surface and the electric field is 90 degrees, 0 degrees, 180 degrees, 45 degrees. Now we know that if this is equipotential surface, electric fields are in this direction, right? So it will be always 90 degrees. So 90 degrees is the answer, right? Equipotential surface and electric field are always at 90 degrees. The electric potential due to a negative point charge at a distance r is, so electric potential due to a negative point charge. So what is the electric potential? It is basically kq by r. Now if the charge is negative, then electric potential due to negative charge will be minus k mod of q by r. Here we are taking only the magnitude, so it is, you can see that electric field due to a negative charge is proportional to 1 upon r, and it is also negative. So, negative and it varies as 1 by r. Option D is correct for this question. Next, the values of electric field E and electric potential V at any point on the equatorial plane of an electric dipole, equatorial plane on the dipole such that. So, if you consider that on the equatorial plane electric field is not 0, right, we have already calculated a few moments back, but electric potential will be 0 because if you consider this is plus q, this is minus q, what happens is that electric potential is a scalar quantity, so they just add like a scalar. So, potential is 0, but electric field is not 0. Option C is correct for this particular question, right. Potential will be kq by r minus kq by r, so it will be total electric potential will be 0. Electric field is not 0. Electric field we have calculated and we found some value, right, but electric potential and on the equatorial plane, on any point on the equatorial plane, will always be 0. So, V equals to 0, but E is not equals to 0. Which of the following is an unit of capacitance? Unit of capacitance: Farad, Coulomb, Volt, Tesla. We know that Farad is the unit of capacitance. Next, a spherical conductor of radius r is carrying a charge plus q. The ratio of electric potentials corresponding to a point on the surface of the conductor and at a point distance 2r from the center of the conductor are in the ratio. So, we have a spherical conductor, radius r. What is the electric potential on the surface? Electric potential on the surface is kq by r, right. Q is the total charge on the surface of the conductor. What is the electric potential at a distance 2r? So, electric potential, this is on the surface, electric potential at a distance 2r will be kq by 2r, right. So, what is the question? Question is surface of the conductor and at a point at a distance 2r from the center. So, surface of the conductor first, next is at a distance 2r. The order is very important. Order, whenever you are finding a ratio, the order of the ratio is very important. Double check it whenever you are solving it. So, first is kq by r is to kq by 2r. So, obviously everything is cancelled except that 2. So, it will be 1 is to 1 by 2, that is 2 is to 1. Okay, so, the ratio is 2 is to 1, option B, not 1 is to 2. Be careful because 1 is to 2 is also given as an option. So, order of the ratio is very important whenever you are solving a ratio based question. The dimension of electric polarization is given by electric polarization is basically dipole moment per unit volume. So, dipole moment is q into 2a, right, that is the formula for dipole moment. Now, unit volume means it will be a cube, right, distance cube is the dipole volume, right. So, this is the polarization P, dipole moment per unit volume, if you remember the formula. So, from here you get this is basically 2q by a square. Now, put the units, 2 is a constant, so it will not come, so only the dimension will come. So, what is q? Q is charge. What is the dimension of charge? Dimension of charge is current into time, right, because current is charge per time. So, from there we can get that charge is current into time, and area a square, a is the length, so it will be L square. So, we get this dimension as L to the power of minus 2, a to the power of 1, t to the power of 1. So, it is this one. So, L to the power of minus 2, a into t is the correct dimension for polarization. In case you forget, you start with from the definition and derive the dimension for yourself. The electric potential at the surface of a charged spherical shell of radius 10 centimeter is 20 volt. The electric potential at the center of the shell is. So, here we have a shell and electric potential on the shell is V is equal to 20 volt. What is the electric potential at the center? So we know that inside a shell or a conducting sphere, electric potential remains constant. V is constant inside the cell. In not only shell, if it is a conductor also, it will be constant, and that value is exactly equals to whatever is on the surface. So electric potential at the center will also be 20 volt. So it will be exactly 20 volt at the center. Any point inside the shell, it will be 20 volt. Any point outside, it will decrease, but on the surface of the up to center, from the center to the surface, it will be constant value. Next, the electric field at a point which is very close to the surface of a charged conductor with surface charge density sigma is, so electric potential on the surface of a charged conductor, it will be sigma by 2 epsilon naught, sigma by epsilon naught conductor, right, sigma by epsilon naught, non-conductor sigma by 2 epsilon naught, for conductor it is sigma by epsilon naught. Next question, the energy density between the plates of a charged capacitor is given by, so energy density is given by half epsilon naught E square, half epsilon naught E square, energy density. So this is the energy, total energy stored in a capacitor. If you divide this by the volume of the capacitor and then if you just adjust it little bit, you will get this value. Derivation is simple, it is given in your book, even though the derivation is not part of the syllabus, but you should know this formula at least. Okay. Next question, an electric dipole is placed in a uniform electric field. The dipole moment makes an angle theta with the electric field. For what angle theta is the potential energy of the dipole is maximum? So potential energy of a dipole is given by minus Pe cos theta. Negative sign is very, very important. Now when the potential energy is maximum, so potential energy will be maximum when the cos theta's value is the minimum value. What is the minimum value of cos theta? Minimum value of cos theta is not 0. Minimum value of cos theta is minus 1. So the potential will be maximum when this is minus 1, so that you get a potential energy Pe. So what is the angle when the cos theta becomes minus 1? It becomes minus 1 when theta is 180 degree. So correct answer is 180 degree, not 0 degree, not 90 degree, but 180 degrees. Okay. Now again fill in the blanks part. I already explained it once. Let's start. A molecule possessing permanent dipole moment is called dash molecule. Molecule possessing permanent dipole moment is called non-conducting molecule. No. Nanofarad molecule, obviously no. Distance molecule, no. Polar molecule, maybe increases molecule, no. Decreases molecule, no. So only possible answer in this case is this polar. So polar we are crossing it out and we will add this here, polar molecules. Okay. Next, the potential due to a dipole depends on, the potential due to a dipole depend on non-conducting, no. Nanofarad, no. Distance, yes. So potential due to a dipole obviously depends on the distance, none other option making any sense. As the distance between the plates of a capacitor is increased, the capacitance, non-conducting, no, distance is done, so cross it. Nanofarad, no. Increases, maybe. Decreases, maybe. So either of them is correct. Either of one of them is correct. So we have to understand this, what happens when the distance between the plates are increased. So capacitance is given by epsilon naught A by D. Capacitance is given by epsilon naught A by D. So if you increase the distance, what happens? Capacitance decreases. So correct answer will be decreases, not increases. Okay, so this will be decreases. Capacitance is measured in nanofarad. Capacitance is measured in nanofarad. Okay, so this is also done. Dielectrics are non-conducting substances. So dielectrics are non-conducting substances. So all 5 are done and you will get 5 out of 5 if you answer in this way. Okay. Now let's move on to the 2 marker questions. What is an equipotential surface? What will be the shape of equipotential surfaces corresponding to a single point charge? any surface which has the same electric potential at every point is called equipotential surface. Any surface which has same electric potential throughout the surface is called equipotential surface. The shape of equipotential surface due to a single point charge is spherical. Single point charge, the equipotential surfaces will be spherical, and at the charge is at the center. Okay, charge at the center and it will be spherical. Now I am drawing circles because this is the two-dimensional plane. In two-dimensional plane, sphere appear to be a circle, right? It is actually out of the page and into the page as well. I cannot draw that, so that's why I have drawing a circle. Now next, on what factor does the capacitance of a parallel plate capacitor depends? So what are the factors on which parallel plate capacitor depends? So they depends on basically mainly two factors, which is capacitance is directly proportional to area, and it is inversely proportional to the distance between the plates. It's the area of the plates, it is distance between the plates. There is one more factor, that is K A epsilon naught by D. Right? What is this K? K is dielectric constant. So if you keep some dielectric medium in between the plates, then also it is dependent on the dielectric constant. So you can write one more point over here, C is directly proportional to dielectric constant. It is capital K. Okay, Coulomb constant is generally represented by small k. Next, write two properties of equipotential surface. Very important question. This is also very important question. Okay, no work is done in moving a test charge over an equipotential surface. Okay, surface and the angle is 90 degrees, so cos 90 is 0. Electric field is always normal to the equipotential surface at every point. I already told you that during the objective MCQ part. No two equipotential surfaces can intersect each other. Your favorite point, right? Same as electric field, no two same electric field intersect each other. Similarly, no two equipotential surfaces can intersect each other, right? Obtain the expression for effective capacitance of two capacitors connected in parallel. This is a 3-marker question. So two parallel capacitor connected in parallel. It can come as a series as well. I am just giving you a hint. Okay, series can also come. So don't say that, sir, you have done only parallel, but in the exam series has come. So you have to study the series part as well. And if you want me to do the derivation for the series portion, please mention that in the comment. I will be doing the parallel one only. Parallel one is the most important. So most important question I am doing in this video. If you want me the series one, which I think is easier than this one, so that's why I am not doing that. So if you want that derivation, please mention that in the comment below. Okay. Now here we have a parallel plate, two parallel plate capacitors. We are considering two parallel plate capacitors. Okay. This one has a capacitance C1. This one has a capacitance C2. This is a external voltage source having a voltage V. Now what is constant for parallel combination? Okay. The thing that is constant for parallel combination is this external voltage. Okay, because this voltage is separately applied to both capacitors. This voltage is separately applied to both capacitors, right? So that is why voltage is constant in parallel combination. In series combination, voltage is not constant. Here, if the total charge which is flowing into the circuit, say Q, then this Q charge will be divided into two parts, Q1 and Q2. Okay, this charge will be divided into two parts, Q1 and Q2, and based on these two charges, the equivalent capacitance can be calculated. Okay, now how to calculate equivalent capacitance? First of all, you have to draw the equivalent circuit. What is an equivalent circuit? Equivalent circuit means everything remains same, only the instead of multiple capacitors, we will replace them with using a single capacitor. This is C equivalent. Okay, so charges are varying, but voltage remains constant. Okay, now we know that from the formula of capacitor, Q1 equals to C1 into V. right? Q is equal to CV. Similarly, Q2 equals to C2 into V, right? If you add them, then what you will get? You will get Q1 plus Q2 equals to C1 plus C2 into V, right? The total charge in the circuit was Q. The same charge will flow here as well, right? Same charge will flow here as well. So from the conservation of charge, if Q charge is going in and Q1 and Q2 are going out, that means from the conservation of charge we can say that Q1 plus Q2 is nothing but Q, right? So what is Q1 plus Q2? Q1 plus Q2 you have calculated, C1 plus C2 into V. And what is Q? From this capacitor we can say that Q equals to C equivalent into V. So it will be C equivalent into V. So V cancels and we get C equivalent equals to C1 plus C2. So this is the equivalent capacitance of parallel plate capacitor. In series case, in the case of series capacitor, okay, the charge will be constant, voltage will be different. Okay, voltage will be different, charge will be constant, but the equivalent circuit will remain same, right? So you have to find Q is equal to CV1, and from there you have to find the V1, V2, and then you have to add V1 plus V2 equals to the voltage V, and same process is same, only in that case you have to find V1, V2 and add them instead of adding the charges will be same in that case. Okay, so that is a hint from my side. Try to do that. The derivation is simple, and if you face any difficulty, mention in the main comment of the video. I will include that in my live session. Give 3 results of electrostatics of conductors. This is also very, very important. Inside the conductor, electrostatic field is 0. Okay, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Electrostatic field, there is a M, one extra M is a typo. Okay, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation, or you can say that any charge given to a conductor will always reside on the surface of the conductor. So this is another way to write that same point. You can mention the other way also. Any charge given to a conductor will always reside only on the surface of the conductor. Okay, so inside of the conductor charge will be 0, but all the charges given to a conductor will always reside on the surface of the conductor. Okay, derive the relation between electric field and electric potential due to a point charge. This is a super VVI question, VVVI, very important question. Okay, and most of you will get this question in your unit test. This is the most common question, and even in board exam also there is a high chance this will come. So here we have a electric field which is pointing upward, okay, and here we have equipotential surface, one equipotential surface, add a voltage V. Here we have another equipotential surface at voltage V minus delta V or V minus dV. Let me use, I don't like delta. Deltas are okay, but not always, so let me use D instead. Okay, differential. So electric field is pointing from A to P, right? Now the distance, we are assuming that the distance dl is very small. Distance dl is very small, so that E equals to constant. So as we know that if you are moving from one point to another, electric field changes its value. But if you consider two equipotential surfaces separated by a very small distance, such that the electric field can be considered constant in this region. So electric field is constant in this region, then what is the force if you keep a unit positive test charge at A? If we keep a unit positive test charge unit positive plus 1, unit positive means plus 1, test charge at A, the force experienced by it is given by Q into E, that is equals to E. Okay. Unit positive test charge Q is 1. So, what is the force experienced by that charge? Force experienced by that charge is Q into E. Okay. Now, if you move this charge by a distance dl in this force field, what is the work done? So, work done is given by force into displacement, that is E into dl. This is the work done, right? Work done definition, force into displacement, E into dl. So, this is from the mechanical point of view. Again, what we know, this work done is basically given by final potential minus initial potential, right? That is the definition in terms of potential. So, both definitions should match, right? From here we get this is basically minus dV. The work done in this case is minus dV. So, work done cannot be different no matter which method you measure in, mechanical way or voltage way, they are, physics is same in both cases. So, that means the work done that you have calculated using mechanical way, that is EDL, must be equals to the work done that you have calculated in the potential way. Okay, basically potential was defined using the mechanical process, right? If you remember the work done to bring a charge from one point to another, right? That's how we defined it. So, here also we are using the same fact that work done cannot be different. So, E must be equals to minus dV by dl. So, this is the relationship between electric field and electric potential. This is the relationship between electric field and electric potential. If the voltage is constant, length is fixed, then it becomes V by L. Now, remember that this in case of multi-directional electric field, it is written more accurately as dV by dx. So, if you have 3-dimensional electric field, then it can be written as Ex equals to minus dV by dx. Okay. Derive the expression for capacitance of a parallel plate capacitor. This is also another VVI question. Okay. Less number of chapters, so all the important questions there is a chance that it will come. So, here we have two parallel plates. Okay, this one having a charge say Q plus Q, this one is having a charge minus Q. Now, remember that parallel plate capacitors, these things are not necessarily to be conductor. So, the electric field due to this is given by sigma by 2 epsilon naught. Electric field due to this is given by sigma by 2 epsilon naught, always nearby. Now, there are 3 regions, region 1, region 2 and region 3. Okay. We have to calculate the electric field in respective regions. Now, if you see that this is a positive charge, what will be the electric field due to this positive charge on this side? This will be in this side, right, E plus. Now, this is a negative charge. What will be the electric field due to the negative charge? It will be towards the negative plate. So, this will be E minus, and both of them have same electric field. So, electric field in the region 1 and in the region 3 will be 0. You have to mention that electric field in region 1 equals to region 3 equals to 0. So, electric field in these two regions will be 0. Electric field inside, now if you consider the inside, positive charge electric field will be away from, negative charge electric field will be towards. So, this will be plus, this will be minus. So, electric field will be in the same direction. So, what is the net electric field in the region 2? Electric field in the region 2 will be E plus E minus, both are in the same direction, that is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is sigma by epsilon naught. This is the electric field due to this charged capacitor. Now if you apply the distance between the plates, suppose the distance between the plates is d, area of the conductor obviously is A, area is A, and the potential difference between the plates is V. Potential difference between the plates is V, right. So what we can say is that Q equals to CV. This is the formula, right. This is the formula. Now if I divide both sides by Q by D equals to C into V by D, okay, or V by D is basically Q by C into A, or it can be done in multiple ways anyway. Okay, let not go into this. I will use the easier way. This will be longer. So first, what we will do, we will use the relation that electric field is basically voltage by the distance. This will be easier. So electric field is basically voltage divided by the distance, dV by dl. Now here voltage is constant in between the capacitor plates, distance is fixed, so it will be V by D. Negative sign we are ignoring for now. So and that will be equals to sigma by epsilon naught. Okay. Now what else? This sigma is what? Sigma is the surface charge density, right. Sigma is surface charge density. So what is sigma? Sigma is charge on any one of the plates divided by the surface area. Sigma is the charge on any one of the plates divided by the total surface area. So it will be Q by A. Put that value over here. So V by D equals to Q by area into epsilon naught. It is also division. Epsilon naught was also in division, right. Now Q equals to A epsilon naught V by D, right. Q is equal to A epsilon naught V by D. Now what is Q? Q is basically equals to C into V. Q is equal to CV, that is the relation of capacitor. So V cancels and we get C equals to A epsilon naught by D. So this is the expression of capacitance for a parallel plate capacitor. This is very, very important to show that electric field outside is 0, electric field inside is this, and then from the relationship of the electric field and potential you can write this statement, okay. So these are the steps of this, and finally just compare it with CV and calculate C. Simple derivation, 3 marks will be guaranteed. Diagram is compulsory for this derivation. Next, now let us move into the 5-mark question. There is only one 5-mark question which is important from this chapter. Derive the expression for electric potential at a point due to a point source charge. Now there may be some other colleges, some colleges teacher want to say test you whether you have studied the entire chapter or not and give you some other derivation as well, but those derivations are not important for majority of the exams that you are going to give. This is the most important derivations from this chapter. So we will study this, and 90% chance is that this derivation comes in your board in your unit test as well. So here we have basically a charge Q, okay. Say this is a bigger charge, so let me denote this as capital Q, and we have a test charge at somewhere, and we want to find the electric potential at this point P. We want to measure electric potential at this point P, right. We have a test charge small q. This is a test charge. This small q is a positive and this is a test charge. Now, if you remember what is potential, the definition of potential was the work required to bring a unit positive test charge from infinity to the point of electric field, right. So, this is the source charge, this is the source charge, that was the test charge. Now, unit positive charge means After calculating everything, if we divide our result by this small q charge, that will give us the unit positive charge. So this q will be cancelled basically. Q is equal to, put q is equal to 1 or divide that by q, whatever you want, that will give us the unit test positive charge. For simplification, I am keeping it as q, okay, so that you don't get confused. Now this small q charge, even though it is located at somewhere, it is not started its journey over here. It started its journey at infinity, somewhere very very far away, and it started walking from infinity, and slowly it reached to a point, at some point, say at a distance x, okay, it reached some point at a distance x, okay. So this is the point, this is where the charge is located now, this is where this test charge is located now, right. Now what is the electric field due to this capital Q at this point? The electric field at this point, Ex, I am saying Ex, is basically given by K, capital Q is the source charge divided by x square. This is the electric field at this particular point. Now this electric field will vary from point to point. Electric field will vary from point to point. At infinity it was 0. As it started its journey from infinity, it reached some inter-between point. This is an inter-between point, it is neither infinity nor our destination P. So for example, a train started from New Delhi and it will reach KSR Bangalore, its destination. So it started from New Delhi, it has not reached KSR Bangalore, it is somewhere say in Yadgir or in Kalburgi or in some other station, okay, Bidar. So it can be somewhere in between these two stations. The starting station was infinity, the ending station is P, but it has not reached at this destination, it is exactly stuck somewhere in between, we do not know exactly, right. Now at this particular point, I can assume the electric field is almost constant, and I will let it go for a small distance dx. Okay, I will let it go for a small distance dx, and I will try to calculate how much work I need to do to bring it from here to here. What is the force acting on this charge? Force acting on this charge, the internal force is acting on this charge is given by, the internal force acting on this charge is given by the charge times electric field. Now this electric field is constant throughout this small distance dx, the very very small distance, one station, okay. So during this duration this is constant. Now when we apply an external electric external force to move this charge, whenever we apply an external force to move this charge, what we have to do? We have to overcome this internal force. We have to overcome this internal force. Our external force will be exactly equals to this internal force, but in the opposite direction. This external force must be equal to the internal force, but it will be in the opposite direction, that is why it is negative. So the external force that we are trying to apply is minus QEX, and whenever we say work done, most of the cases it is the work done by us, that is why we always apply external force. So what is the work done to bring this charge by us for this small dx distance? So what is the work done? The work done will be given by the external force that we are applying times the displacement. External force that we are applying times the displacement, that is minus QEX into dx, or minus Q, what is Ex? Ex is given by this, so it will be KQ by x square into dx. So this is the work done, small work done, okay. Or let me rewrite this, minus KQQ by x square dx. This is the small work done to move this charge by this small distance dx, okay. Now that is not our target. This small work done, we are not here to calculate the small work done. We are here to calculate the total work done, total money required to travel from New Delhi to KSR Bangalore. That's what we are interested in. A 5 rupee ticket can take you by one station, 10 rupee ticket can take you maybe 2 stations. But we want to calculate the total fare from New Delhi to Bangalore, right? For that, what we have to do? We have to calculate the total work done. The total work done is basically, what is the trick? It started at infinity. It will reach at point P. Now, distance of point P, obviously it is not given. Distance of point P is small r. Distance of small p is small r. Okay, so we are trying to reach at Bangalore station. We started at New Delhi, so that will be our total work done. This will be our total work done. So from here we calculate infinity to r. Infinity to r, we have to put this value. There is a negative sign. The negative sign we will keep it outside the integration, then we will put all the values k, q, q, x square dx. So here we are doing the integration with respect to dx. So remaining everything else will be constant, right? So they can go out of the integration, k, q, q integration dx by x square. Now let me know in the comment below if integration is done, completed in your college or not. In case it is not done, you can go and check my bridge course where I have discussed about integration, how to do integration, basic integration formula, right? Here the integration value will be minus k q p q, it will be minus 1 by x. Now I am not doing the detailed integration over here. I have already explained it multiple times why it will be minus 1 by x. If you are not sure, you have to learn about integration. Once the integration is done, this is a very simple integration. You will do lot of difficult type of integration in your mathematics, right? Now let's put the values over here. So this minus will again come out, and it will this minus and this minus will become plus. So we get k capital Q small q. Now first will be upper limit, that is 1 by r, minus the lower limit 1 by infinity. Now what is 1 by infinity? 1 by infinity is nothing but 0. So we get this as k q q by r. So this is the work done to bring the charge from infinity to this point. This is the fare, right? Now from the definition of electric potential, this is equals to the total potential at this point. So this is the potential at this point. So from here we can say the potential is basically for q is equal to 1, unit positive charge. If q is equal to 1, if q is equal to 1 in this equation, that will give us the electric potential. So potential will be k q by r. Okay, q is equal to 1 is very, very important to remember, or potential is given by 1 by 4 pi epsilon naught q by r. Okay, this derivation is super important. Okay, it came back to back here twice in your board exam. Back to back here twice it came in your board exam. There is a chance again it will come in this year as well, but there is a high chance even if it does not come in your board exam, it will come in your unit test. Okay, now let's see some numerical question. Two numerical question from this chapter. Calculate the potential at a point P due to a charge 400 nanocoulomb located 9 centimeter away. Okay, so first we have to calculate the potential P due to a point charge 400 nanocoulomb located 9 centimeter away. So here we have a 400 nanocoulomb charge, and we are trying to find the potential at a distance 9 centimeter away. This is our point P. So what is the electric potential? Simple formula, electric potential is k q by r. Yes, as simple as that. K is 9 into 10 to the power of 9, q is 400 nanocoulomb, that is 400 into 10 to the power of minus 9. Distance is 9 centimeter. So whenever there is a centimeter given, you convert it into meter by multiplying 10 to the power of minus 2. This is always better. Okay, instead of going into the decimals, 10 to the power of minus 2 method is always better. Okay, so you get here it as 4 into 10 to the power of 4. Okay, 4 into 10 to the power of 4. How did I get that? If you are interested, let me show you. 400 divided by 10 to the power of minus 2. So it will come up and it will become 10 to the power of 2. So here we had 2 zeros and 10 square. So it becomes 10 to the power of 4. This is part A. This is part A. Now what is part B? Obtain the work done in moving a charge of 2 nanocoulomb from infinity to the point P. Does the answer depend on the path which the charge is moved? So what is the work done to move a charge? Work done to move a charge is basically the potential energy of the charge at that point. So potential energy of the charge is equals to the work done. So what is potential energy? Potential energy is charge times the value of the potential. So charge is 2 nanocoulomb, 2 into 10 to the power of minus 9. Potential is 4 into 10 to the power of 4. So it will be 8 into 10 to the power of minus 5. Okay, joules. Okay, unit you have to be careful about units. Potential is volt. Potential is easy, potential's unit is volt, so that will be easy for you, but here the unit will be joules. Okay, now what else? Does it depend on the path? Is there any dependency on the path in the formula? Obviously not. There is no dependency on the path because it's potential energy. That means it only depends on the initial and final point, does not depend on the path through which it follows. Conservative force, this is the property of conservative force. So it is independent of the path taken. You have to be careful. This is a part question. It is given in the question, so you have to mention that as the answer. Okay, you have to mention that as the answer. If you do not mention this, then it will be 1 mark will be deducted from your final answer, right? So 4 into 10 to the power of 4, 8 into 10 to the power of minus 5. It does not depend on the final path taken, any path taken, right? So you have to be careful. You have to mention that. 3 capacitors, let me check, there is a page. 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination. Find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. So what are the capacitors? 2, 3 and 6. So we have 2, 3 and 6 all connected in series. Two microfarad, 3 microfarad, 6 microfarad. So first part is to find the equivalent capacitance. So in case of parallel combination, the equivalent capacitance, series combination equivalent capacitance is same as parallel combination of resistors. So it will be 1 upon C1 plus 1 upon C2 plus 1 upon C3. That will be 1 by 2 plus 1 by 3 plus 1 by 6. So it will be 6, 3 plus 2 plus 1, so 6 by 6. So it will be 1 microfarad. So the equivalent capacitance is 1 microfarad. Very simple. Now what? Now they said what is the potential difference across 6 microfarad capacitor. Okay, this voltage is given 60 volt. Then what is the voltage drop across this? this one we have to calculate. Okay. For that, first of all we have to calculate the total charge that is passing through this capacitor. How to find the total charge? Equivalent capacitor is already calculated. So, from there we can calculate charge. Charge equals to C equivalent into the voltage. So, charge will be equals to C equivalent is 1 microfarad, micro means 10 to the power of minus 6, okay, times voltage is 60. So, it will be 60 into 10 to the power of minus 6 coulomb. So, this is the total charge that is passing through each of the capacitor. Series combination, charge will be constant. The same charge will pass through this one as well. Okay, charges are conservative, isolated system. This is an isolated system. So, whatever charge is going into this capacitor, same charge will go into the other capacitor, and so forth and so on. Now, for this capacitor, if the voltage is V, say V1, if the voltage is V1, then Q, same Q will be equals to C6 V1, okay, C6 V1. Now, 6 into 10 to the power of minus 6 V1 we do not know, we are trying to find that, but charge we have already calculated. So, let us put that 60 into 10 to the power of minus 6 cancels, and V1 equals to 60 by 6, that is 10 volt. So, voltage across 6 farad capacitor is 10 volt, and whenever you are trying to solve the numerical question, write down the answers in the end as a sentence form. That will be beneficial for the teacher. Whoever is checking, he will be careful and not miss out any of the answers that you have written. So, 1 microfarad, this is part A and this is part B. So, we have completed the second chapter as well. Now, let us move on to the next chapter, electric charges and field. This is electric current and potential, right. Now, here just before going into this chapter, I am not going to do any numerical from this chapter, electric current, because electric current numericals are typically difficult, okay, and I do not recommend the numerical question from this chapter even for your board exam as well, okay, because there are a lot of circuit analysis you have to do. If you are personally good with circuit analysis, you can try to solve some of the circuit analysis question from your NCERT textbook or from previous year questions. Otherwise, I recommend you to avoid this because I have observed 80% of the student, they think it is easy, but they fall in the trap, they make some mistakes. You have to be very careful while answering numerical questions from the current electricity chapter. Okay, so if you want me to solve current electricity chapters numericals, and mention that in the comment below, I will try to incorporate that in the live session, as I am going to do that live very soon. Okay. Dates will be announced on our YouTube channel. So, if you have not subscribed to our YouTube channel, definitely subscribe and join our WhatsApp channel as well. Next, statement 1, the resistivity of metals increases with the increase in the temperature. So, resistivity of metals increases with increase in temperature. So, this is basically correct. Resistivity depends on temperature, and if you increase the temperature, resistivity increases. Increasing the temperature of metals cause more frequent collision of the electrons. Yes, so more frequent collision means the free path between the electron decreases. Okay, that's why the relaxation time decreases, and that's why the resistivity increases. So both statements are correct, and it is basically correct explanation as well. So option A is correct. So statements 2, statement 1 both are correct, and statement 2 is the correct explanation of statement 1. Identify the wrong statement from the following. Now, wrong statement, I have made it capital. It may not come as capital in your exam, so you have to be careful and identify if it is wrong statement or correct statement. Wrong statement means 3 of the statement are correct, only 1 of them is incorrect. The drift speed acquired by free electrons per unit electric field is called mobility. Yes, that is the definition of mobility. Mobility is Vd by E. So, drift speed acquired by free electrons per unit field. So, the language may be little tricky, but it is the definition of mobility. The conductivity of semiconductors decreases with increase in temperature. So, conductivity of semiconductors decreases with increase in temperature. So, if you increase the temperature, conductivity of normal conductors decreases, but for semiconductors it increases. Semiconductor behaves opposite to that of a normal conductor. That is why this is the wrong statement. This will be our answer as well, but you can check the other two options as well. I always say that even if you find the correct answer, check the other options as well. Be patient, don't be in a hurry. The conductivity of conductors decreases with increase in temperature. Yes, conductivity of conductors decreases with increase in temperature. Same statement as I said, it is true for conductors but not for semiconductors. Alloys are widely used in construction of standard resistors. Nichrome, okay, alnico, they are all the conductors, they are used for construction of standard resistors, right? Manganese. So, they are all alloys and they are all used in construction of standard resistors. So, this is also true. Next question, a wire has a non-uniform cross-sectional area as shown in the figure. A steady current I flows through it. Which one of the following statement is correct? So, as you can see here we have a non-uniform cross-sectional area conductor. Okay. So, this is A, this is B. Now, let us see what are all the options given. The drift speed of electron is constant. So, drift speed of the electron is constant. Now, drift speed is given by Vd equals to I by NEA, right? I by NEA. I is constant. Current I is independent of the basic drift speed. Okay, it depends on I, V and R. Right. So, I is a constant, but area is not constant. As you can see, area changes, that means Vd will change. So, Vd is not independent of area and it is not constant. The drift speed of electron increases while moving from A to B. So, as you are moving from A to B, as you can see, the area here is less, area here is less, area here is more. A has smaller area compared to B. Smaller area means larger drift speed, larger area means smaller drift speed. So, drift speed decreasing, not increasing. The drift speed of electron decreases while moving from A to B. Yes, this is the correct statement, as the electron is moving from A to B, because increasing in the area, drift speed decreases, not increases. The drift speed of the electron varies randomly, which is obviously a simple option, can be ignored. So, option C is correct. So, this is a very tricky question, higher order thinking level question. You have to be careful to answer such questions. The resistivity of a metallic conductor dash with decrease in temperature. Okay, the resistivity of metallic conductor with decrease in temperature. So, if you decrease the temperature, the resistivity also decreases. So, resistivity also decreases. If you increase the temperature, resistivity increases. You decrease the temperature, resistivity decreases. Kirchhoff's junction rule. Kirchhoff's junction rule is a reflection of. Junction rule means where some currents are going in, some currents are going out. So, what is this rule is reflection of? This is a reflection of conservation of charges. This is a conservation of charges principle. Okay. In the absence of an electric field, the mean velocity of free electrons in a conductor is at absolute temperature T is. So, no electric field is applied. So, you are trying to find the mean velocity of electrons. So, mean velocity of electrons will be 0. Mean velocity of the electron will be 0. Okay. If you apply external electric field, then only there will be some drift velocity, otherwise mean velocity, random motion, it will be 0. Ohm's law is valid when the temperature of the conductor is very low, very high, constant, varying. So, one of the constant of Ohm's law is temperature and other physical constant remain same. So, that means temperature must be constant for the Ohm's law to be valid. In the equation AB equals to C, A is the current density, C is the electric field, then B is. So, what is A? A is current density and B we do not know, C is electric field. Okay, then what is the value of B? So, JB equals to E. Now, we know that J equals to sigma E. J equals to sigma E. So, from here we can write is that E equals to J by sigma, okay, or 1 by sigma is basically rho, resistivity rho. So, here B is resistivity, B is resistivity, not resistance, not conductivity, not potential difference. So, this is definitely the resistivity. This is a one way to answer simple question. They just make it complicated to make it a HOTS question. This is again a HOTS question. The relaxation time in conductors increases with increase in temperature, decreases with increase in temperature, is independent of temperature, changes at 400 K and above. So, as we say, as if you increase the temperature, electron starts moving rapidly. Rapid motion means more collision means relaxation time decreases. Okay, relaxation time means when the electron is not having any collision and he is relaxing, like you right now. You are not having any exam most of the time till now and you are relaxing, right. So, electrons are also relaxing. Now, as soon as the exam dates are approaching, you are thinking what to study, how to study. So, now you are opening your textbook and started studying now. So, similarly, if the temperature increases, the relaxation time decreases. So, relaxation time decreases with the increase in temperature. With the increase in temperature of the conductivity of semiconductor increases. So, again increase in temperature increasing means semiconductor conductivity decreases and metals increases. So, metals increases and semiconductor decreases. Option B is the correct answer. So, resistivity related questions are very common from this chapter. So, there will be one question from resistivity from this chapter, maybe semiconductor, maybe metals, maybe combined both of them. Okay. So, 10 MCQs are done from this chapter. We will do more MCQs from all the 3 chapters in our live session that will come very soon. So, please subscribe to our channel if you have not yet subscribed and join our WhatsApp channel for the updates. Now, in a current carrying conductor, now time for fill in the blanks. In a current carrying conductor, the net charge is dash. So, in a current carrying conductor, the net charge is mobility, energy, charge, electric resistivity, 0, superconductivity. So, only one thing that makes sense is if this is given as 0. So, net charge is 0. Even if it is a current carrying conductor, the net charge is still 0. The magnitude of the drift velocity per unit electric field is mobility. We have seen that is the definition of mobility. The SI unit of dash is ohm meter. Whose unit is ohm meter? Ohm meter is the unit of resistivity. It is the unit of electric resistivity. The resistivity of a certain metals or alloys drops to 0 when they are cooled below a certain temperature. This phenomenon is known as superconductivity. If you decrease the temperature at certain temperature, the resistivity becomes 0. They are called superconductor. They can conduct electricity without giving any resistance, and they are called this property is called superconductivity. The Kirchhoff's loop rule is based on the law of conservation of energy. Loop rule is energy, junction rule is charge. Okay, so loop rule will be energy. Short answer type question, not objective question, short answer type question for 2 marks. Let's see, define drift velocity and mobility of free electrons in conductors, or then maybe one more question, define mobility, mention its SI unit. Both are 2 mark question. So drift velocity, the average velocity with which the free electrons drift under the influence of an electric field is called drift velocity. Mobility, the mobility of free electron is defined as the drift velocity of electron per unit electric field applied. So you can say that it is basically drift velocity by E. Okay, the SI unit of electron mobility is meter square second inverse volt inverse or meter second inverse Newton inverse Coulomb. So basically what you are doing here you are using the unit of velocity meter per second, and unit of electric field is Newton per Coulomb, but because it is in the division, so Newton is inverse, Coulomb is simply there. Okay, this is another unit volt. So if you apply volt per meter and one of the meter will be multiplied over here, so this is another unit. Any unit you can write, that is no problem, as long if you understand the formula, if you put the units and whatever unit you are getting, if you write that, that is also very, very good. Mention two limitations of Ohm's law. This is also common question. Ohm's law is applicable only if all the physical conditions remain same. So what is the meaning of that? Physical condition means state of the matter. Suddenly you are applying a current through a conductor, it melts, becomes liquid. Ohm's law will not be valid in that case. So all the physical conditions remains the same. Ohm's law is not applicable at very low and at very high temperature. Even if the temperature is constant, but if the temperature is very, very low or very, very high, Ohm's law will not be applicable. Ohm's law is not applicable to non-ohmic devices like semiconductor devices, discharge tube, etc. Okay, they are called non-ohmic devices. Give any two differences between current and current density. Okay, what is a current? Current is defined as the amount of flow of electric charge per unit time. Unit of current is A. Current density is the amount of current per unit area. Unit of current density is ampere per meter square. This is also very, very important. This question came in the objective as an objective 2 years back. So units you also have to remember. Current is basically amount of charge, whereas current density is current per unit area. Okay, symbol is J is equal to I by A. And obviously it is I is equal to Q by T. Okay. Next, name two factors on which the resistivity of a metallic wire depends. Resistivity, not resistance. Resistivity depends on material of the wire and temperature of the wire. Okay, whereas resistance depends on rho L by A. So resistance depends on length of the wire and inversely proportional to area, right? But resistivity does not depend on length or area. Okay, this is resistance, this is resistivity, this is resistivity, and this is resistance. This resistivity sometimes also called as specific resistance. Okay, this is called specific resistance. So if you hear the name specific resistance, don't get confused. Specific resistance and resistivity are same. Write the expression for drift velocity in terms of current. Explain the terms used. Okay, so what is the drift velocity? So first I equals to NEA VD, or VD equals to I by NEA. What is I? I is current. This is drift velocity. VD is VD drift velocity. I is current, N is number density of electrons in the conductor, okay, E is charge of an electron equals to 1.6 into 10 to the power of minus 19 coulomb. A is the area of cross section of the conductor. Right? Derive the expression for drift velocity in terms of electric field and relaxation time. So, here you have to derive the relationship of drift velocity in terms of electric field and relaxation time. So, first we have electric field applied over here, electron is moving in this direction, electrons are getting drifted. So, let us see. Now, to do this derivation, we will start with our known formula I equals to NEA VD, right. This is the known relationship between current and drift velocity, and then if we try to find VD, we can write this as I by NEA, right, or it can be written as I by A by NE. Now, what is I by A? I by A is current density. So, VD equals to J divided by NE. Now, what is J? J is sigma E, that is the other form of Ohm's law, into NE, right. So, you have to do it step by step. Now, from here you have to put the value of sigma in terms of relaxation time. These two formulas you have to remember. Okay, this formula, this sigma is obviously it is easier, but this sigma formula also you have to remember. It is given by N E square tau by M. Okay, N is basically number density, E is the charge of electron, tau is the relaxation time, and M is the mass of an electron. M is the mass of the electron. You can write this as ME as well. So, now N cancels, one of the E will be cancelled. So, you will get drift velocity will be equals to E tau by mass of electron. This is the required relationship between drift velocity, electric field and relaxation time. Drift velocity, electric field and relaxation time, this is the relation, important relation, 3 marks only for you, remember the formula. Okay. Also, if possible, mention that in the bracket sigma is equal to N square tau by ME. Also, you have to mention what are all the terms. Okay, what are all the terms? If you mention that, you will get full marks. The diagram is optional. I have just given it because it is given in your textbook. Now let us move on to the 5 marker question. Two cells of different EMFs and different internal resistances are connected in series. Derive the expression for effective EMF and effective internal resistance of the combination. Parallel combination may also come. You have to practice that. I am doing the series one. Okay, so parallel one also I am going to do anyway. So, both I will be doing, series and parallel both I will be doing. Also I will be doing the Kirchhoff's not Kirchhoff's law, Wheatstone bridge. Okay, so these 3 are the important derivations from this. So, first is a cell and its internal resistance. Cell means they will always have an internal resistance. Okay, here we have another cell, another resistance. I am doing 2 only. Okay, you can add more than 2 also. Generally they mention 2 cells in series and always there will be an external resistance. 2 is easier. More than that you have to just adjust it anyway. So, this is epsilon 1 R1, this is epsilon 2 R2, this is capital R. The current in the circuit is I. Now, what is this? Is the 2 cells in series, right? Now, if you draw an equivalent circuit, what is the beauty of equivalent circuit? Equivalent circuit will have the same current and the components will remain the same. Okay. So, it will have the equivalent EMF and equivalent resistance. Okay. So, first we have to find what is the current in this circuit. So, for that we will apply Kirchhoff's voltage law. So, current I in the circuit, it is so how many resistors are there? R1 and R2, all of them are in series. Total voltage is epsilon 1 and epsilon 2. So, from there we can say that I into R plus R1 plus R2 equals to epsilon 1 plus epsilon 2. Okay, you can consider this to be Kirchhoff's voltage law or Ohm's law, no matter what, you will always get this, right. Now, what we will do, we will try to find I into R. I into R is our main target, and here we will get this IR equals to epsilon 1 plus epsilon 2 minus I into R1 plus R2, right. This is the voltage across this resistance, IR, right. This is what we have found from the normal circuit. Now, same thing if we apply for the equivalent circuit from equivalent circuit. Okay, from equivalent circuit, same current will pass, current will remain same. So, again R and R equivalent are in series. So, again from the Ohm's law, R plus R equivalent equals to epsilon equivalent. Again we will try to find the same thing, IR equals to epsilon equivalent minus I into R equivalent. Okay. So, this is equation number 1, this is equation number 2. So, if you compare these two equations, if you compare equation 1 and equation 2, you will see that this value is exactly equals to this, right. So, epsilon equivalent, that is equivalent EMF is basically addition of the EMFs, and similarly R equivalent equals to R1 plus R2. So, this is the equivalent EMF for two cells in series. Okay. Now, let us move on to the two cells in parallel. Two cells in parallel. Now, in case of parallel, what is constant, by the way? This is the basic theory for all types of circuits, maybe resistance, maybe capacitor, maybe cells, does not matter. The main thing is same, that is the voltage remains same in parallel combination and current remains same in series combination. So, this is epsilon 1, this is R1, this is epsilon 2, this is R2. Okay. Suppose I1 current pass over here, I2 current pass over here, and total current is I. Okay. So, first again we will use the, now this case the equivalent circuit will be simple, same simple R epsilon equivalent R equivalent. Okay. So, this is the equivalent circuit. Now, here it is easier for us to apply Kirchhoff's laws, okay, Kirchhoff's loop rule. So, first we will take this loop, okay, the outer loop. Okay, this, say this loop is loop 1, this is loop 2, and each case we will take this R is common, this loop is common. Okay, we will start from this and we will pass through R and we will go. So, from loop 1 what we get? So, first we are the current passing through the resistance is R, is I. So, IR. Next is we have to go to the this. So, what is the current? I1, and it is passing through small r1. So, plus IR1 equals to the EMF connected in the circuit. This is the first part. From here we will try to calculate the I1. So, I1 R1 equals to epsilon minus IR, or I1 equals to epsilon 1 by R1 minus I R by R1. Okay. Now, similarly we can calculate I2, right, same formula, same method. Similarly I2 will be epsilon 2 by R2 minus I R by R2, right. So, we have calculated I1 and I2. If you add these two, what you will get? You will get the total current I. So, if you add these two, you will get total current I, okay. I equals to I1 plus I2. So, I equals to epsilon 1 by R1 plus epsilon 2 by R2 minus I R 1 by R1 plus 1 by R2, okay, minus minus common over here. Now, what we will do, there is a I, there is another I. So, what we will do, we will divide everything with this, divide everything with this. So, what we will get? I by 1 by R1 plus 1 by R2 equals to epsilon by R1 plus epsilon by 2 by R2 divided by 1 by R1 plus 1 by R2 minus IR. Okay, this IR was still there. We have divided it. Now, we will separate the IR part. So, IR is basically given by epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2 minus I by 1 by R1 plus 1 by R2. This one now comes over here. Our target always to calculate IR, right. So, again in this circuit, if you calculate IR, you will get IR equals to epsilon equivalent minus IR equivalent. Okay. So, this is the basic formula. So, from here we can calculate this one will be epsilon equivalent. So, epsilon equivalent is basically given by epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2. You can simplify this, but I recommend you to remember this like this. This is easier to remember, and R equivalent is given by 1 by R equivalent. It will be, because you have to adjust this epsilon equivalent minus I by 1 by R equivalent. If you see that here the resistance is coming in the division. So, similarly here also you have to apply this here. So, it will be 1 by R equivalent equals to 1 by R1 plus 1 by R2. So, this is similar to parallel combination, right, of resistances, and here it is a special unique formula. This requires some amount of steps, and this is also very very important. It came in the board exam as well and in the college exam as well. So, you have to practice it once and write it down 2-3 times, so that you are ready for this. This is the really tricky derivation. Arrive at the balanced condition of Wheatstone bridge using Kirchhoff's rules. So, balanced condition Wheatstone bridge. Wheatstone bridge has how many resistors? 4 resistors. Okay, each of them are like this. Now, the trick I am going to teach you is very 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 simple. So, this is say P, this is say Q, this is R, this is S, and here in between we have a galvanometer. Suppose total current in the circuit is I. It is breaking into 2 parts, I1 and I2, and then some part of the current is going through the galvanometer, some part current coming over here. Okay. So, say this is I3, this is say IG, this is say I4. Okay, I am not doing any Kirchhoff's current law over here, because I will show you some simplified simple trick for this derivation. Now, for balanced condition of the bridge, what is the balanced condition means? Balanced condition means through this galvanometer there is no current. This is a circuit. If voltage at this point and voltage at this point, these two points are equal. So both points are at equipotential, that means no current will pass. No current will pass through this galvanometer. So for the balanced condition, what we can say is that Ig is equals to 0. So if Ig becomes 0, whatever current is going in, the same current will go out. So I1 will be equals to I3 and I2 will be equals to I4. No current is getting added over here. Now what we have to do, we have to find the total voltage over here and total voltage over here. Now if you see the question, what you have to be careful, you have to apply Kirchhoff's rule, that is the question. So to apply Kirchhoff's rule, first of all, Kirchhoff's current rule we have partially applied, so that part is done. Now we have to apply KVL. So how can we apply KVL? To apply KVL, we have to consider this one loop and this second loop. So first we will take this loop, this is loop number 1, this is loop number 2. So for this loop, what is the condition? So I1, okay, I1 into P, P is the resistance, I1 into P. So I1 into P, there is no current over here. Then again from here to here, we are going in the opposite direction of the current. So opposite direction of the current means it will be negative I2 into R. Okay, I1 into P minus I2 into R, and there is no battery connected in this particular loop, so it will be 0. So I1P equals to I2R. Keep it as equation 1. Okay. Now again we will take the second loop. So you will start from here. So now here I3 is equals to now I1. So instead of writing I3, I will be directly, this is loop 1 and loop 2. Loop 2 will be I1 into Q minus, again same thing, we are going opposite direction, I2 into S equals to 0. Same thing. So I1 Q equals to I2 S. So this is equation 2. Right? Now divide equation 1 by equation 2, we get I1 P by I1 Q equals to I2 R by I2 S. Obviously I1 I2 will cancel, and you get this as P by Q equals to R by S. This is the condition for balanced Wheatstone bridge. So simple easy derivation, no one will going to give you this simple easy derivation, okay, and as you can see that if you practice this, you can master it very quickly. This question came last year. I am not expecting this question to come in your board exam, but this question there is a high probability it will come in your midterm exam, okay. And if you are watching this video for the first time, definitely I will request you to subscribe to our channel and like this video if you find this video helpful for your unit test preparation. I will be back with the live session very soon. Till then, bye.